So, up until now, we've really only been talking about correlational design, which only gives us the ability to determine whether two variables are related, whether they go together. But in order to determine if a variable is causally related to another one, or one variable causes the other one, the only way to do that is through an experimental design. So, in an experiment, you are purposely manipulating variables rather than manipulating ones that already exist. The goal is to isolate cause, or to be able to say with confidence that variable X causes variable Y. To be able to say that we have cause, there's a few key factors that we need to be able to sort of check off or say that we've satisfied these conditions. And there's three of them: random assignment, temporal precedence, and manipulation of the IV with use of control groups. Don't worry, we're going to break those all down next. Let's take a second and talk about random assignment. In order to do an experiment or to have true experimental design, you need to have at least two groups, and you want those groups to be as equal as possible. Now, you might be wondering why that's important. Well, earlier I gave the example about blood pressure, so let's use that again. So we have, just to refresh your memory, we have two groups of participants. One group gets an exercise plan, one group gets a medication plan. Okay, so the question becomes, who is in which group? Who gets what? Who gets the exercise? Who gets the medicine? So we need to create two groups. Well, an easy way to do that would be to just divide by gender, right? So we could say men go into one group and women go into the other group. Easy, simple, pretty much straight down the middle, no problem, right? Wrong. That's actually not a great way to do it. The issue is that if we were to divide our groups based on something like gender, we would be able to be certain that any changes in our dependent variable, which is blood pressure, are due to the independent variable, the exercise or the medication. They might also be due to gender differences. Right. So if basically what we're doing by creating that sort of uh, systematic difference in our two groups is we're shooting ourselves in the foot before we get started. What we want to do instead is have two groups that are as similar as possible across as many dimensions as possible. Things like age, gender, race, socioeconomic status, education, health. We want two groups that look almost identical. What that does is it sort of levels the playing field. It wipes out all of those differences in things that could be potentially confounding. So once we have our two randomly assigned groups, we then determine which one gets which level or condition of the independent variable. One is going to become the experimental group. They're going to get the manipulation. Usually, this is something like an exercise plan, a treatment plan, a specific drug, a type of therapy. The other one becomes the control group. Now, you might be wondering, what's the purpose of a control group? What's the point if we're not actually giving them anything? They're not getting a manipulation. The control group is actually there for a comparison. If I were to just take 100 people with high blood pressure and give them blood pressure medication, how do I know that the blood pressure medication did anything? I have nothing to compare it to. I need a control group or a comparison group that didn't get the medication. Then I can compare the two groups and see, is there change between these two groups? So, say we are developing an intervention to increase adolescents' knowledge about safe driving. We create an interactive game. It's going to help teach them the rules of the road, and we want to see if it helps to reduce the number of accidents. So we take our group of participants, we randomly assign them to one of two conditions, either the PowerPoint slides or the driving game. You might be wondering, what's our independent variable? What are we manipulating? If you guessed that it was the condition, the game versus the PowerPoint, or the type of educational materials, you would be spot on. What are we measuring? What's our dependent variable? If you guessed the number of accidents, once again, you would be right. So in this case, we would give the interactive game to our experimental group. We would give the slideshow to our control group, and then we can compare results on the number of accidents to see which group did better, which group had fewer accidents. In a study like this, we would probably predict that the driving game condition, so the participants who were exposed to the driving game, retained the information better and probably had fewer accidents. That would be our prediction. Now, I mentioned earlier that the only way to determine if one variable is causally related to another is through a true experimental design. So remember, with correlation, all we could do is determine whether two variables are related, but true experimental design lets us take that next step. And so there are three characteristics that we need to be able to determine causation. Covariance, basically just asking, is the independent variable related to the dependent variable? Temporal precedence, does the independent variable come before the dependent variable in time? Is our cause and effect moving in the right direction? And internal validity. Are there alternate explanations for the results? So we're going to go through each of them in detail, but I want to use an example to help us do that. So some researchers at Cornell University conducted an experiment to see if the size of a serving bowl had an effect on how much pasta people ate. And so participants were randomly assigned to be in either the large bowl condition, which is our experimental group, or the medium bowl condition, which is our control group. Then they took part in a kitchen laboratory-based lunch. And so participants would serve themselves from a communal serving bowl, either a large bowl or a medium bowl, depending on the condition they were in. What's our independent variable here? What are we manipulating? You guessed bowl size. That is correct. We are manipulating the size of the bowl. We have a large bowl condition and a medium bowl condition. Our dependent variable would be the amount of pasta that each participant consumed. That's what we're measuring. We're not changing anything with the amount of pasta served. The only thing we're changing is the bowl size, and we want to see if that impacts the amount of pasta consumed. So each participant would serve themselves from one of the two bowls, depending on their condition. Their plate was weighed before they ate the pasta and then weighed again afterwards to determine how much they ate. So now remember, we have two groups of participants. The control group is going to serve as our comparison. So for this example, let's say that the medium bowl group is the control, the experimental group is the large bowl. So the question becomes, does the size of a serving bowl cause a change in how much pasta people consume? Before we can answer that question, though, we have to determine whether or not this study meets the criteria for causal design. So our first criteria is covariance between the IV and the DV. Covariance is asking if the variables co-vary. Do they go together? That's all it's asking. This is essentially asking about correlation. If the two groups ate the exact same amount of pasta, there's no covariance. Serving bowl size wouldn't influence how much pasta people ate because it was the same in both groups. So you might be wondering how we determine that. We can look at the mean level differences in terms of how much pasta people ate. So on the horizontal axis here, we see the bowl size. So the pink bar is going to be the medium bowl. The blue bar is the large bowl. On the vertical axis, we see the amount of pasta consumed. What do you notice right off the bat from looking at this graph? What you're seeing is that the blue bar is higher. Participants in the large bowl condition ate more pasta than those in the medium bowl condition. This is good. This is what we want to see. If these two bars were the same, imagine they were the same height. What that means is that the bowl size doesn't matter. People ate the same amount of pasta regardless of the bowl. In that case, it would no longer make sense to ask if bowl size causes a change in pasta consumption because there was no difference in pasta consumption. So there has to be mean level differences between the two groups. They have to co-vary. They have to go together. Hope you can't see it, but we have a little check mark showing that the covariance condition has been met. But we still need to check our two other conditions. Temporal precedence is just a fancy way of saying which one came first. We're talking about cause and effect. So if we want to say that X causes Y, we need to clearly demonstrate that X came before Y in time. Kind of that age-old problem of the chicken and the egg. And so we need to be able to know which came first. With something like this, with a study like the example that we're using, it's sort of built into our design. They experience the bowl size first, then they eat the pasta. So chronologically, we know that the bowl manipulation is coming before the amount of pasta consumed. But take an example like, does social media engagement impact loneliness? Just by measuring the two of those variables, we don't know which one is which. There's a lot of different ways we could address temporal precedence in that example, but perhaps the most straightforward is to look at change over time. So maybe we measure social media engagement in January, and then we measure loneliness in February. And so we see, does social media engagement impact loneliness? In that case, social media would come first because we measured it first. So we need temporal precedence to be able to get past that association claim. So again, because of the way that this study was designed, we are all set. We are good to go. We know that the serving bowl size manipulation came before the amount of pasta consumed. Two conditions down, one to go. Now, hopefully you remember earlier in the week when we talked about confounds, which are alternative explanations for the change in the dependent variable. You need to be able to rule out as many different confounds as possible in order to be able to feel confident that the independent variable is what's causing the change in the dependent variable and that it's not some other variable. So, can you think of any potential confounds? And remember that confound question. What factors other than the IV might impact the DV? Or in the context of this example, what factors other than bowl size might influence the amount of pasta consumed? Think of any? Off the bat, I'm thinking about how hungry they are. Somebody who ate a full meal before they came into the lab is probably not going to eat very much pasta, regardless of the size of the serving bowl. I'm thinking about things like weight. Okay, smaller people tend to eat less. Things like health, eating disorders. People with disordered eating patterns are probably going to eat less pasta, again, regardless of the size of the bowl. This is also a really good example of how the two conditions have to be very similar. So imagine the medium bowl condition has this delicious looking, fettuccine Alfredo pasta with this yummy sauce, and it's nice, soft, fluffy pasta, and it looks delicious. The large bowl has, marinara sauce, but it's kind of dry and crusty and doesn't look very appealing. People are probably going to eat more from the medium bowl, not because of the bowl size, but because of the quality of the pasta. In a study like this, we would need to make sure that the pasta in the two bowls looks exactly the same, that it's both hot, that it's both fresh in the exact same ways. Otherwise, we're introducing a confound. Random assignment does help with internal validity quite a bit. It does help us level the playing field, but we'll never be able to say 100% for sure that we've controlled for every possible confounding variable. Really, all we do here is we do our best to say that we have tried to account for every potential confound that we can think of. Once we do that, then we say that this condition has been met and that we have established internal validity. Now, thinking about some of the pros and cons of experimental research, obviously the major pro is that it permits causal conclusions. It lets us isolate cause between the IV and DV, asking if social media engagement causes loneliness or bowl size causes more pasta eating. True experimental design is great. It helps us do a lot of things in our research, but it's not perfect. There's always going to be some issues with confounds or outside influences that can change the effect of the IV and the DV. There's also the placebo effect. Have you heard of this? Ever have a headache and you take Motrin and you say, I'm going to feel better now because I took that medicine? Yeah, our brains are powerful and we can easily be fooled by things like this. So what we do in experimental design, we have to make sure that we're keeping those two groups similar. So if we're doing a drug trial, we would give a sugar pill to the control group. Or if we're doing an alcohol intoxication study, we would give the experimental group alcohol, but we would give the control group orange juice or something like that. The thing with experimental design is that we can't manipulate everything. Some things you literally can't manipulate, things like gender or I won't say impossible, but they're very, very difficult to manipulate. And some things are unethical to manipulate. Take sexual assault, for example. If that's something I'm interested in studying people who have experienced sexual violence in their lives. I can't randomly assign my participants and say, okay, group one, you're getting assaulted. Group two, you're not. Not ethical. And we'll talk in a later lecture about ethics in research and the Institutional Review Board, but they absolutely would not approve a study like. So I'm going to give you a couple examples, and I want you to identify the design. Is it experimental or correlational? And what's the independent variable and the dependent variable? So researchers are interested in the influences of self-esteem. Participants are given a set of anagram puzzles to solve in a 5-minute period. Half are randomly assigned to receive very easy anagrams, half get very difficult anagrams. After completing as many of the anagrams as they can, participants are given a questionnaire labeled Thoughts and Feelings Questionnaire, actually a measure of self-esteem. So pause the video, experimental or correlational, IV and DV. This is actually an experimental design. And what should tip you off to that is the random assignment. Okay, we have two groups. They are randomly assigned. Different things are happening in each group, and then we are measuring something. What is the independent variable? Think about what's happening in the two different groups. One group gets very easy anagrams, the other half gets difficult ones. We're manipulating the difficulty of the puzzle task that they're being given. And then we're measuring their self-esteem. That's our dependent variable. We're probably interested in whether or not having a difficult test makes you feel worse about yourself. A pair of psychologists are interested in the effects of mood on helping. They give some random people free tickets to a happy movie, and then they have a confederate or an actor drop papers in front of the people who just got out of the movie, and also in front of people who are only walking by and have not just seen a happy movie for free. The researchers then watch to see if the participants help pick up the dropped papers. Experimental, correlational, IV, and DV. Pause the video, think about it, and then when you come back, I'll let you know the answers. Hopefully you got that this is also an experimental design. We have two groups of participants once again, the group who got the random free movie and the people who did not. This one's a little bit dicier because the random assignment isn't quite as clear, but this is definitely, we have two groups. We are manipulating a variable, we're manipulating the movie. Okay, so the priming effect of that happy movie. And then the dependent variable, what we're measuring is helping behavior. Dr. Young examines how older males and younger males portray themselves on dating apps. She systematically reviews profile pictures of men of different ages on Tinder and notes if they tend to post pictures of just themselves alone or with a group of friends. Correlational, experimental, IV, and DV. This one's actually correlational. We are not manipulating anything. And the way that you should know this is because when we look at the variables, we're not actually changing anything. All we are doing is measuring two things that already exist and comparing them. So what are those two things that we're measuring and comparing? If you see age, you'd be correct. And picture status. Okay, so is there a relationship between age and the way that we post pictures online? So this is a correlational design. And so that is about it for true experimental design. We're getting the crash course. If you want to learn more, take research methods. But for now, that will suffice. And so in our next lecture, we're going to talk about ethics. It's very important to be ethical researchers and make sure that we're treating our participants correctly and we're not causing undue harm. And there's a lot of things to think about that go into that. So we'll talk more about that in the next lecture.